Good morning. This is my third lecture in the series. Just one moment, please. Yesterday we discussed deep machine learning and deep learning, and I considered one elementary application of it. So I have two very interesting applications. One to do with detection of features in galaxy images, and another was the classification of stellar spectra. Now, the classification of stellar spectra is ongoing work. We have just completed one large project on it and entered into another project to do with what are known as mu spectra. But unfortunately, I will not be able to go into that because of lack of time. So I decided to look at bar detection in galaxies briefly, and after that I'll go to the third part of my talks, okay, which is precision measurements in astronomy. So bar detection in galaxies. So now here is everybody's dream of a picture of a galaxy. So it is a well-known galaxy called M51, which, as you see, is a almost completely face-on spiral. So you know that there are two kinds of galaxies, mainly three kinds of galaxies. One, the elliptical galaxies, which appear to be ellipses when projected onto the sky. And then there are the lenticular galaxies, which have a very large bulge, which looks like an elliptical galaxy, and they are surrounded by a disk. And then we have the most familiar type of galaxy, which is the spiral galaxies. So like the lenticulars, they have a bulge and a disk, but the disk has more or less wonderful spiral arms in it. Now you see that the bulge in these galaxies is rather small, but the disk is very prominent. The disk is a flattened structure, and the spiral arms are present in it. So M51 is a good example of such a galaxy. Now here are three more galaxies, and when you compare them with M51, which is at the bottom left-hand side of the figure, so you'll see that the other spiral galaxies all have, there are two spiral galaxies on the top, and the one at the bottom is a lenticular galaxy. And you see that toward the center of the galaxy, you can see a very clearly defined linear structure. Now this linear structure is known as a bar in the galaxy. And if you count all the galaxies and see what fraction of them have bars, you'll find about 40% of them have these bars. And bars are very prominent, like the one which are shown here. Otherwise, they could be less prominent. Then you may even find it difficult to decide whether a galaxy has got a bar or not. Now, the important point to understand, even though very briefly, is that bars are very important features in the galaxy. So they may be born in galaxies out of internal interactions. And what the bars really correspond to dynamically is that there are orbits of stars which are placed along the bar. So in general, the stars would be moving either in the bulge or they'll be moving in the disk of the galaxy. But when you've got a linear structure known as a bar, the stars have distorted orbits. As a result of the presence of the bar, you can funnel matter from the outside of the galaxy to the inside. And what kind of matter are we talking about? It is gas, but you could also funnel stars to the internal regions. Now, this transfer of matter from the outside to the inside actually leads to evolution of the galaxy. So therefore, bars are very important objects. And we would like to really find bars. The way people do it is, of course, traditionally is for experienced astronomers to look at large numbers of galaxies. And then, as I said, many bars are very prominent. There's no problem there, but other bars are not so prominent. And then it becomes more difficult to detect them. So the question is, can I now train a system? Can I train a neural network for the detection of these bars? So what is the problem that we are faced with? We have got an image of a galaxy, and it could be, even if you take a small cutout of the galaxy, you could easily have a 100 by 100 pixel image. So you're talking of 10,000 pixels. And what would be, I'm sure by now you'll appreciate what would be involved in the training. So I will take a large sample of galaxies, about half of which have bars and half of which have no bars. Then I'll pass these images to the network. And then each time I expose a galaxy to it, I'll say, this is barred, this is barred, this is not barred, this is not barred, and so forth. So that if I give it thousands and thousands of galaxies, okay, then it will train itself. And then the idea is that if I then give it a bunch of galaxies to which it has not been exposed, then the network should able to tell me which of these are barred and which of these are not barred. Right? So what are the difficulties that you are faced with? The first difficulty is the large image sizes. So which means that a fully connected machine learning network would be very hard to design and to run. Not so hard to design, but to run it, it will take a lot of time, and the numerical computations will be very, very tricky. So this is really a great example of an application of deep learning networks. Because the deep learning network will look at the image, and then instead of looking at it pixel by pixel, it will look at it like you look at a human face, meaning that, oh my God, this galaxy has got a linear structure in it, right? So then because the linear structure is present, I call it a bar. So which means that it has to learn to recognize linear structure. Then it has to learn to be not distracted by the spiral arms. So you may find here that the spiral arms are actually away from the linear structure. But if you look very carefully, look at it here. The spiral arms really are starting off from the end of the linear structure. So what can happen is that even when a bar is not present, if the spiral arms can conspire together to call it a bar. So then why don't we call this bar-like structure a bar? Because it is not dynamically a bar. So if you actually go to the literature and look at well-defined images, good galaxy images, which have identified bars in them, and galaxies which have been identified as not having a bar, you find that the sample is rather limited in number. Okay, meaning that you'll typically find a couple of thousand of each kind. So now you could spend a great deal of time trying to make a bigger sample. But for that, you'll require experts, you'll require a lot of time, you'll require a lot of resources, which you may not have. So how do you manage the thing then? Because your deep learning network would need maybe 10,000 galaxies. So then you resort to what could be thought of to be a subterfuge, but one can show that it is perfectly a legitimate thing. And just look at this particular galaxy. So you see that when you are looking at, say, real life images, let us say that we are training the deep learning network to recognize dogs. Right? So, but then you know how many different kinds of dogs there are. And then if you just show it faces of dogs and nothing else, that is one. But when you just show it dogs, there will be dogs which are sitting, dogs which are standing. There will be a Labrador which is running and an Alsatian which is doing something else. So you really, for proper application, you really like to teach everything, I mean, to train the neural network to be able to recognize all dogs in all these contexts. So what you do is that you get different kinds of pictures with dogs in them. You don't have the luxury here. We have only 2,000 galaxies. So what you actually do is that you take a galaxy like this, and you take the image and you rotate it by a degree, and then you rotate it by another degree, and then you rotate it by another degree. And then you'll find that you can generate a lot of images like this. So you take your 2,000 sample of 2,000 galaxies, and then rotate them by whatever degrees that you want, each one of them. And if you take 10 images of each, then instead of 20,000, 2,000, you got 20,000. So you may say, this looks like nonsense to me. Because what happens if I just take a galaxy like this, and I get any number of images that to train the whole correct, except that you will train it to recognize just those two galaxies. Right? So you see then you have to strike a balance. You have got to have a large enough number of galaxies to have a variety in them. And then, given this variety, you are increasing the sample through through this rotation, and that is called image augmentation. So when you are stuck with a small number of samples, there are many different ways in which this augmentation can be carried out. Okay, so I have finished all this. So you see that here is the sample of galaxies, right? And then you can see that these are, now let me see, I have to remove things which are covering the image on my screen, right? So these are these are images of galaxies, and these are one more. Yes. So you'll see that um, on the left side, you'll see there's a number of unbarred galaxies. On the right-hand side, you'll see barred galaxies. So you see here, for example, is a rather small galaxy, and the bar is not completely obvious. Whereas here, it is completely obvious. Whereas here, you really can't say offhand whether it is a bar or whether there are spiral arms just sticking in there. Right? So that has all been carefully done by the people who worked on this project. Right? And then here is a network. I showed you this Alex. It's an AlexNet convolutional neural network. I've already shown you a picture of this, and the person who led this investigation was Shilu Abraham. Uh, and then she is now in Kerala teaching in a college. And then you see that there are 12 layers with 5 convolutional layers. Okay, this is what she used. Great. The power is gone, but it'll come back. Doesn't affect the talk as far as I know. Right. So the training sample of 2,700 galaxies and the barred galaxies, um, uh, it had 2,704 barred galaxies and 2,741 unbarred galaxies. Right. So then, now when you train the network, then what you do is that you've got the training sample. The part of your sample of barred and unbarred galaxies is set aside as a test sample, and then you have got the rest of the objects which are gone into the training. The test sample is not to be exposed to the deep learning network during training. It has to be completely untouched beforehand. And then what you do is that you say, all right, I take my trained things, then I take my test sample, pass it through the network, let the network decide whether this is barred or not barred, and then I compare the prediction of the network with the answer that I already know. And how did I get the answer originally? The answer came through experts on galaxy astronomy who actually looked at large samples and decided which are barred and which are not barred. I mean, obviously, every step is prone to error, and it's a sort of a bootstrapping that you do. Right. So here, what the confusion matrix does is that it gives you on the x-axis, there's a label which is predicted by the deep learning network, and on the y-axis, you've got the true label. So you see that this one here, the upper left-hand corner, in the matrix element 1, 1, you will find that 1100 galaxies which were barred have actually been classified as barred. And here, 1100 galaxies which are barred have been classified as unbarred. And what is this? So this is known as true positives, and this is known as a false negative. I mean, those which are not barred have been classified as unbarred. And here you have got the barred, unbarred, barred. So these are what are called true false positives. And then here you have got unbarred galaxies classified as unbarred, which are the true negatives. So you see, the idea would be to decrease these positives, false positives, as much as possible. Because if you don't do that, then I go and tell somebody that, look, I got 1,157 barred galaxies. There will be how much is this? So this is a 5% contamination. Okay, because 11 galaxies is 1%, so 50 is about 5%. So I would say that my accuracy is 95%. Okay, so now here I am missing out these galaxies. So when I miss out, then the inclusion is less, right? So you report the results in in thing like this. Recall. Recall means I am able to recall all the barred galaxies. Did I recall all the barred galaxies? No, I lost 57. So this recall is 95%. Okay, and the precision. Okay, meaning how many did I miss? I missed 14%. So recall is better than for the unbarred galaxy. So you see that both the recall and precision are high. And what is the average number that we get? 94 and 94%, which is actually considered to be pretty good for a thing like this. Okay, so here are some examples of galaxies which are known previously to be unbarred, but which have been classified as barred. And then sometimes what happens is that you go and look at the original classification when you have got sufficient confidence in your network, and then you say, my God, this is not all right. Okay, so it is a bit of a give and take in everything. And this picture, which I will not spend any time on, tells you what happens is that when you pass these galaxy images through different kinds of filters. So you see that this filter, for example, is picking up certain features. This figure is picking up some other features. And what you must understand, where does the learning come in? The learning comes in because you have not defined the filter. All that you have told the deep learning network is that please use 15 filters or 20 filters or whatever. And you also say use the size of the filter to be used. And it is for the network actually to decide which are the useful filters. So now what is the analogy to this? When I showed you the elementary machine learning examples, um, when we had a straight line as the solution, we could really think of it and give it a straight line and do it. But when we had a complex curve as a solution, it would be really impossible for us to give any equation, meaningful equation for the curve. But we did not have to give that equation. It is that in the process of training, the neural network learned what is the correct appropriate curve. So please remember that as an important takeaway, that in the process of learning, the network is really doing things which you have not, uh, is following paths which you have not charted out for it. Okay, so now I'm afraid that I'm going to have to leave this spectral classification of stars, and some other day maybe we could do it again. So what I'm going to do now is, like, sometimes you change trains when you're going from one place to another. We used to do quite a lot of that when we were young. I'm going to change my presentation. Okay, so now I have gone to precision measurements in astronomy. All right. So now I spent quite a lot of time over this one picture, this thing in the first lecture. So just to recapitulate, we started off measurements with Hipparcos measurements in 150 BC with a positional accuracy of 1000 arc seconds. And then we made our way to a positional accuracy of a milli arc second. And then I just mentioned the micro arc second precision. Right? So, so, so now this is a nice picture of the Gaia mission. So let me try to move this out of the way. Picture of the Gaia satellite, which is already there in the sky. Right, so so you see that here the accuracy reached by Gaia, as I told you, is about 1 micro arc second positional accuracy. And how many objects do you have? Just look at this here. The position and brightness on the sky. So there's actually 1.6 billion stars, because this, as you see, is 10 raised to 9. Okay, so 1.6 billion stars. And then the colors, parallaxes. Well, parallaxes, as you may have already heard, gives you the distances. You've got parallaxes. So you've got the stars, you've got the positions, and then you know how the positions change as the Earth goes around in its orbit, which gives you the distance to the stars, and then you have got the proper motion. Okay, meaning that how is the star moving in the sky? is there a motion to it? And then because you have got the distance and you have got the proper motion, it means that you will have a three-dimensional image of the sky. And in this case, the image is mainly limited to our galaxy. That was the whole point of Gaia, is to map our galaxy in as much detail as possible. So it says that positions of brightest stars measured with 5 microarc second accuracy. So now I want to move to examples of precise measurements in astronomy. I'm not going to use Gaia as the example because I have not yet worked on that. So, but you see that there are two terms which you will come across in measurements, and you will do well to understand this precisely. I'm sure many of them know these terms already, but let's take a quick look at them. So these two terms are precision and accuracy. So what do you mean by that? Let us suppose that I'm trying to measure a quantity here, which is shown, just a one-dimensional quantity. And let us say that here, this is the reference value. Okay, reference value meaning I know that this particular quantity has a certain value. So let us say that we are measuring the magnetic field of the Earth, then it will be 0.36 Oersted or whatever. Or if I'm looking at a period of a pulsar, the rotation period of a pulsar, I could very easily determine it to 10 places of decimal. Okay, and so that is my 10th place of decimal, 15th place of decimal, and that is my reference value, which are called a true value, because there's no such thing as a true value. There's only a reference value. So now supposing somebody else now makes a measurement. Now they may do it even more precisely than I did it, or they could do it less precisely, and which is typically the case, because there are these reference measurements which are made very, very carefully, and the other measurements may not be done so carefully. So then you see that if I go and make the same measurement any number of times, and then I can plot the measurements I got for this value, I can make a plot of it, plot a histogram. And typically, as all of you know, I will get a Gaussian distribution. So why do I get a Gaussian distribution? It is because of the random errors which are present in the system. So let us leave it at that. We get a Gaussian distribution. Now, if I'm not careful with my measurement, then if the measurement is, let us say, 0.36 Gauss, say I may get a value 0.28, 0.48 or whatever, and in which case my Gaussian would be very broad. Whereas if I make very careful measurements, use very accurate instruments, then the Gaussian will become narrower and narrower. So therefore, when I present the measurement to you, I could say that it is 0.36 Gauss plus minus 0.1 Gauss. Okay, which is, so what is 1 Gauss, 0.1 Gauss is what is the 1 sigma error. So the error is about 5%, which is less measurement. So then what would I say? I would say that my precision is not good enough because I am not being able to pin down my measurement. But now if I measure the magnetic field with an accuracy of 0.01 Gauss, so then I'm really talking about 0.36 plus minus 0.01 Gauss. I'm getting an accuracy of 3%. So then what will happen to the Gaussian? The Gaussian will shrink. So therefore, the more precise is my measurement, the smaller are my error bars. The narrower is the region in which I can say that my value lies. But however however precise my measurement would be, you'll see that it is quite different from the reference value. So why did that happen? Now it could be because I am using faulty techniques. So even though my measurements are precise, I am not allowing for certain systematic errors in the system. Right? Because there are many different things to go making a complex measurement. For example, I'm measuring the temperature of the cosmic microwave background. That's a very, very, very complex measurement. And there I would end up, I could be making certain assumptions which are not valid, which give me a wrong answer. So the difference between the mythical true value and the value that I get The difference between that determines the accuracy. And then when I make a prediction of when I give you a measurement, the precision determines what is the spread of my measurement. So please keep that in mind. All right. So the first one is Hubble's constant. So I am one of the last persons to lecture in this series, and then and so I can depend on my colleagues having told you so much about astronomy. I'm sure you know what is Hubble's constant by now, but I'll just explain it very very briefly for the sake of completeness. So we go back to our image of M51, and this is a galaxy, and then this is Andromeda, and those are the big images that we are used to. But when we go to something like the Coma cluster, which is a large cluster of galaxies, then everything that you see here is a galaxy, and many of them actually belong to the Coma cluster. So how would I know definitely that the galaxy belongs to the Coma cluster? For that, I would have to determine the distance to the cluster. I would have to determine the spread of the cluster. And then if a new galaxy is discovered in this field of view, then if it is at that distance within that spread, then I would say that it belongs to the Coma cluster. So you see how important it is for us to determine distances. And then here are is a rich cluster, and which is about 1,000 galaxies. Now nearly every galaxy in the field of the Coma cluster you can make out the galaxy. But then now look at the Hubble deep field. It's an extremely small area of the sky, 7 square arc minutes. Okay, now this is very long ago. It was an ultra long exposure, 30 hours at 606 nanometers, right? And then this field was chosen in such a way that it does not have too many stars. Here is clearly a star because you can see the diffraction spikes. Here clearly are the galaxies. But the marvelous thing is that every small dot in this picture is actually a galaxy rather than a star. And then how many are there? If I ask you to estimate, you may say 200. But when you count them, you'll find 3,000 objects in this. Most of those are not being seen here. Okay, so you'll have to do very, very careful measurements to find all those objects. Right, so the person who really studied galaxies well is Edwin Hubble. There's another person involved, and I'll come to that person quite soon. But this is Edwin Hubble. You have heard of him before. And so what he did was that he actually studied hundreds of galaxies. And then you know that when you study new things, like Darwin was studying all these plants and animals, the first thing that he did was he classified them. And after the classification, he developed a theory of evolution. So that is the standard path followed in all the sciences. So what Hubble did was that he collected images of a large number of galaxies, and then he developed his tuning fork diagram. Realized that there are elliptical galaxies, lenticulars, and spiral galaxies, and so forth. And then he made precise measurements on these galaxies. Okay, so and then so you see that here you see the lines of the galaxies. This is this line here is actually the spectrum of a galaxy, right? And on the spectrum, on the bright spectrum, you'll see these dark bands, which are absorption lines. These are not absorption lines, most of them produced in the galaxy, but the absorption lines produced by the individual stars in the galaxy, which are superposed on each other, right? And then the white lines that you see are the arc lines in the laboratory. So these arc lines, you know what the wavelengths are, and then you look at the lines in similar positions, and then you measure their wavelength, so you know which elements are present. But when Hubble was doing that, when Slipher was doing that in 1912, that is about 10 to 15 years before Hubble's work. So he had already discovered that these lines are redshifted. Okay, meaning that what do you mean by redshift? Means that the line is supposed to have particular wavelengths, but in this case, they found that the wavelengths had that corresponding lines had larger wavelengths in some galaxies. So what is that due to? It is very straightforward to interpret that as a Doppler effect. So you know what's a Doppler effect? So if I got a source of light emitting a fixed wavelength which I'm observing, and that source of light begins to move away from me, then all of you know that the wavelength will increase, right? And then that wavelength increase is known as the Doppler effect. If the source of light moves towards me, the wavelength decreases. So the reddening of the light is known as the redshift, and then the light becoming bluer is known as the blue shift, right? So then, what is the formula for that? You can see it here. Is that if lambda E is the emitted wavelength and lambda O is the observed wavelength, then lambda O upon lambda E is equal to root of C plus V upon C minus V. This is a standard special relativistic formula, and it can be derived using special relativity. There is no cosmology coming into the picture. So then I define a quantity. Let us suppose, so you see that lambda O upon lambda is defined to be 1 plus Z, where Z is known as the redshift. So if V is positive, meaning it is moving away from me, the redshift is positive. If V is negative, meaning the object is coming towards me, then Z is negative. And then if you use for V much smaller than C, if I use the binomial theorem, then I'll find that Z is approximately equal to V by C. Right, so when Hubble, Slipher had already made these measurements, and then you would already have guessed that it's the Doppler effect. And then what Hubble did was that he went further. He obtained the redshift for a fair number of galaxies, a big data. The large data. Large data means how much? About 20 galaxies in this picture. But it really took him extraordinary effort to gather this sample of galaxies, which was very large for that time. And then what did he do? He made a plot. I will move this around. So he made a plot of velocity of recession against the distance to the galaxy. And you see that clearly, you look at these points now, there seems to be a linear relation there. And so when Hubble went and fit his linear relation to it. And then he gave a law. What he said was that the velocity of recession is equal to a constant, which we now write as x0 in honor of Hubble, times d. And what is d? D is the distance. So you immediately have got a marvelous tool here. So this tool is that if I can, you see that there are a number of galaxies. I can look at the spectra and I can measure from the observations and comparison with the laboratory measure the velocity of the galaxy. And therefore, since I know x naught to be 500 kilometers per second per megaparsec, I know what is the distance of the galaxy. So Hubble had invented a new method for measuring distances, right? So now there are different sides to the story. First of all, look at this particular galaxy here. And this is not a galaxy which was known to Hubble. The technology will permit him to do that, to observe this galaxy, but we do now. And we look at this galaxy. So you see that it's a rather vague kind of object. And what is the redshift? It is 11. So if Z is equal to V by C, it means V is 11 times the velocity of light. So you say, what nonsense is this? It can't be true. Special relativity doesn't permit it, right? So then you really need not special relativity, but general relativity to interpret this kind of a result. And in general relativistic cosmological models, what you get is that there is something which is known as the scale of the universe, okay, which is a representative of how large the universe is. Now, one of the things that Hubble did, he not only made a measurement of the distance, provided a measurement technique for the distance, but Hubble also discovered, I mean, if you go back to this picture here, you see that the further a galaxy is away from us, the greater is the velocity, right? Now that has its own implication. So we are now sitting here in the Milky Way, and we look at all the galaxies expanding from us. But the Milky Way has no special role to play, and therefore if I shift to any other galaxy, I should again see that galaxy, all the galaxies moving away from that galaxy. So how is this interpreted? Hubble interpreted it as the cosmic expansion of the universe, that the whole universe is expanding. So that was a marvelous thought. And it is that which is known as Hubble's law. This fit is not Hubble's law. The Hubble's law is that the universe is expanding. Right? So here you've got the scale of the universe, and then the fact that the redshift is positive means that the universe is expanding. And then when you interpret it in terms of general relativity, you find that over large distances, you cannot assume that V is much smaller than C, and then that whole expansion is not legitimate. Have the full in relativistic. All right. Why is Hubble constant so important? Because it sets the scale of the age of the universe. The age of the universe is approximately equal to 1 upon h naught. The scale of the universe is equal to c upon h naught. And there is a quantity known as critical density, which is very important for cosmology. That is also determined by Hubble's constant. Now, you must please understand that if a billion years from now, astronomers make a measurement of the Hubble's constant, they will get a different value. So it's a Hubble's constant, there's a Hubble's constant for our epoch. And that is what this knot is indicating. So the Hubble's constant is very difficult to measure, and it has got a checkered history. And so you see that here in 1930, when Hubble made the first measurement, the value was 500 kilometers per second per megaparsec. By 1980, the value had reduced to about 100. So you have to keep moving this one here, about 50. And then you'll find that in the inset, you'll find that when I go to 1990 to 2010, it has concentrated to about 70 with a narrow spread. I will, before I explain what the implication of that, let me introduce you to other very fine gentleman who is known, who was the Abbé Georges Lemaitre. So he was a Swiss, no, he was a Belgian priest, and then he did cosmology, and then he was really totally marvelous figure in the history of science, because you see that well, one moment, I want to read out the whole title for you and move this thing away. So, his full title will be the Reverend Monsignor Georges Lemaitre. Okay, so so he in a paper published in 1927. So remember that Hubble published his work in 1930, 1931. So in 1927, the paper was in French. He rediscovered the Friedmann equations for the dynamical evolution of the universe. The Friedmann equations had already been discovered by Friedmann. Then he showed that the expansion of the universe implies that the spectra of galaxies are redshifted by an amount proportional to the distance. So he had got the Hubble relationship. He used published data on the velocities and photometric distances of galaxies to derive the rate of expansion of the universe. So he did everything that Hubble did, but he did that before Hubble did. So why did they not call it the Lemaitre law? That's simply because it was in a French journal which not many people were reading. And then he was in communication with Hubble, and it is believed that in one of the early International Astronomical Union General Assemblies, he actually met Hubble and discussed the matter with him. And then Hubble published his work, but there is no reference to Lemaitre's results there. Right? So then Lemaitre was asked to translate his paper into English, and it appears in the monthly notices. And then Lemaitre did one amazing thing. He said that, look, I have a diagram which shows that velocity is proportional to d. Now Hubble has the same diagram, and Hubble diagram is better than mine. His data is better than mine, more numerous than mine, and therefore I will not include that part in my paper. So the most important result, which he had discovered independently before Hubble, is left out. But in spite of all that, he has got his due now in recent times, and in the General Assembly in Vienna in 2018, the IU resolved to recommend that from now on, the expansion of the universe be referred to as the Hubble-Lemaitre law. It's very nice to understand these historical things. You must lose their perspective. All right. So now here is uh, a modern plot. And when was this done? In 2001. It was a HST, Hubble Space Telescope key research. And then you see what you have here. There are many new measurements there made there. And here you have got the distance, and here you have got the velocities. And Hubble's thing would have been, on the basis of which he derived his law, would have been somewhere here, the lower left-hand corner. That's all. And how do we get all these distant measurements? There's a Tully-Fisher law, there's a fundamental plane, there's surface brightness fluctuations, there's supernovae 1A and supernovae type 2. So what are all these? I'm sure somebody will ask me the question. So I got a box here which explains very briefly what those are, but I'll not go into them. And then, what is the current value of Hubble's constant? It is 73 kilometers per second per megaparsec, plus minus 2, which is a random measurement, and plus minus 4, it is systematic. So where does the random measurement come from? It comes from random errors of measurement, but which are very complexly carried forward. And where does the systematic come from? You see that all these objects, different kinds of things have gone into calibrating the distances, and they'll all carry their own assumptions and problems. And so the estimate is at 4. So we know the Hubble's constant value to be 73, and within 73 plus minus 7, you can plus minus 6, you can say. So this is a pretty precise result there. But the question is it accurate? Meaning that after all, Hubble gave a value of 500, we went to 50, now we are climbed back to 73. So how confident are we? There is already trouble on the horizon, but the trouble is very delicate. It is not very gross, meaning we are not going to go back to 500. But you see here, that these are measurements. The blue ones are what are known as astrophysical measurements. Okay, meaning what? All the methods that I showed you now. The red one are cosmic microwave background measurements. Okay, these are measurements used made through the measurements of the fluctuations in the cosmic microwave background, and these are Planck results. And then you see, so the red ones are Planck. These in the green color, sort of green color, are WMAP. And then, so you see that again, each one of them, these measurements, as well as the astrophysical measurements, carry small error bars. So they are both precise measurements, but there's no mixing. Meaning here, this error bar goes from there to there. So this time, this one could be the same at the same Hubble value, except that the errors of measurement are much larger. Here, the errors of measurement are much smaller. So this group claims that this is the correct value. This group claims that theirs is the correct value. Right? So the accuracy is about 5 out of 75 is about accuracy. And which group is correct, to my knowledge, is not yet well established. Great. So I'm now going to the last part of my talk, which is supermassive black holes in the Milky Way. Right? So I've got about 15 minutes left. I should be able to do it in that. So these are measurements which have been made over a long period of time, meaning that the first measurements were reported in 1993. And there are two groups which worked on them. A group by Genzel, led by Genzel, who is a director of the Max Planck, one of the Max Planck Institutes in Max Planck Institute for Extraterrestrial Physics in Munich. And Gez, where is he? I mean, he's in the US. And Genzel first used, he has used European telescopes, including the VLT, and Gez worked with the not TMT, he worked with the Keck telescopes. Right. So what is the issue that they addressed? So here's a picture of a galaxy, Milky Way Galaxy. It is just a superposition. It's what you call it. You are panned. You are sitting inside the galaxy and panned with a near infrared camera, and then you can see the bulge and you can see the disk. And you're not seeing the full extent of the galaxy because these are too faint to be observed, right? So the end-to-end thing of the galaxy is about 30 kiloparsec. Okay, there are 100,000 light years end to end. And what we are interested in a very small region at the center of the galaxy. And you must remember that the sun is about 8 kiloparsec from the center of the galaxy. So then I'm sitting here 8 kiloparsec away, and I'm looking at the galactic center. And it is very difficult, it would be very difficult for me to observe individual stars in the galactic center for two different reasons. One is that there are all the brown patches that you see are patches of dust. The dust dims the light from the stars. So the stars become about 8 magnitudes fainter by the time you go to the, not intrinsically fainter, but apparently fainter, when you go to the center of the galaxy. And then the second problem is that as you go to the center, the field gets more and more crowded, so there's a mixing of the stars. So then how do you resolve this problem? One is that you make measurements at near infrared wavelengths, because at near infrared wavelengths, the absorption is reduced to the minimum possible. Second, you use techniques for for deconvolving the stars. Meaning, like I told you, and so many other people that I told you, the stars have got a diameter, a full width at half maximum about 1.5 arc seconds in these measurements. Uh, and then where the intrinsic size of the star is much smaller because they are so far away, and you can use techniques to resolve them, resolve the stars, reduce the spreading, which are known, the technique that you use here, the most important technique is adaptive optics. I'm sure Ram Prakash and others have told you about adaptive optics. So what is the challenge that what Gaz and Genzel uh, worked for? They said that we want to go to the center of the galaxy, and then at the center of the galaxy, we want to measure the orbits of stars. So what do you mean by the center of the galaxy? There's actually a radio source called Sagittarius A, okay, which are discovered, I believe, in the early 1970s. These are three component or multiple component source, and one of them is known as Sagittarius A star. And Sagittarius A star is at the center of the galaxy. What do you mean at the center of the galaxy, and how do you know it is the center of the galaxy? It is, you can say, the mass centroid of the galaxy. And then, so here, the picture that I showed you was taken at radio wavelengths, and here is a very nice picture of the same thing, taken by the Chandra X-ray Observatory at X-ray wavelengths. And you see that here, this red blob that you see covers Sagittarius A star. Sagittarius A star is there. And in fact, in this zoom, you'll see that this is the center of the galaxy. This is Sagittarius East, this Sagittarius West. And this thing here, when my cursor arrow is sitting down, is Sagittarius A star. So we look at what the VLT did. As you know, the VLT has got 4 telescopes. They give marvelous names in the local language. And then the 4 of them, each is a 8.2 meter telescope. And then all these 4 telescopes were eventually used in the measurements. And here are the Keck telescopes, which are twins. There are 2 Keck telescopes, each 10 meters in diameter, currently the biggest telescopes in the world. And you see here is, come on. So here is actually a picture of the center of the galaxy. It's a HKL composite, meaning there are 3 near infrared wavelengths, the composite of that, and something called speckle interferometry and adaptive optics have been used to resolve the images here. And then you see that this rectangle here is the center of the galaxy. No, is a thing that, sorry, there is a arrow here which is covered. I don't want to do too much. Okay, you can see here now, right? This is 6 light months. So this rectangle is about 3 light months. So I told you that the size of the galaxy can be taken roughly to be 100,000 light years. So we come to 1 light year, and then we come to half a light year, right? So this is a very, very small portion of the galaxy. And then you see here, now that is zoomed, and this is Sagittarius A. And what you see here is something truly marvelous. Okay, and so you see that you are now seeing individual stars in the center of the galaxy. And then there is one particular star here, S2. Okay, so we are going to follow the motion of the star S2 over a period stretching from 1993 to something like 2000, 2019. Okay, so that's a long period of time, 26 years. So, so then now here you will see that these measurements have been done on the stars, and the arrow shows the direction in which the star is moving. Okay, so which means that there are multiple measurements which are involved. So now let us see quickly what would be the problem in making measurements like this. So you see that you started in 1993. The paper was written in 1999, and in 2003, the first paper that I'm going to be referring to. Right, so you went on measuring for 10 years. Now these are measurements at a milliarc second scale. Right, so now you see that I take a image of the galaxy and I look at the stars. I take image 6 months later, 1 year later. Now you see that when I want to compare those positions, you must please understand, and this is very, very important, is that you have to hold the coordinate system constant. Right? Because if your coordinate system in each image changes, which it will, in the measurements it does changes, but you have to be able to transform them all to the same set of coordinates. Now that requires very, very great deal of work and very, very great deal of precision. So that kind of precision is not available optically. So what they do was that they take a small number of maser stars here. It is that stars which are emitting maser radiation. And radio astronomers are extremely good, the telescopes are extremely good at very accurately measuring the positions of those stars. So they provide the fundamental frame. And then the optical frame is fixed relative to that. And I'm emphasizing this because my talk is on precision measurements in astronomy. So after you did all that, then then you see they have now this star S2, which has been followed from 1992 here to 2002. 10 years of observation. And what do you get? You get a most marvelous ellipse. So now you must understand that a very similar result was obtained about 400 years before that for the orbit of Mars. So I mentioned Kepler to you, and Kepler was given the data on Mars, and Kepler decided that it is an elliptical orbit. Now his problems were different. He did not know what was the equation of an elliptical orbit. He derived the equation, didn't realize what he was looking at was was actually an ellipse, and again spent many years after that before he published his result. Right, so you see that the same thing, the orbit of star S2 is this marvelous ellipse, and there's an object sitting at the focus, at one focus of the ellipse, just like the sun sits at one focus of the ellipse along which Mars is moving. And then applying Newton's law of gravitation, we determine the mass of 3.7 billion solar masses. So you see that how marvelous this measurement is, that you have done that and you have got the mass. And then what can this be? Can it be an extended object? It can't be, because when the object is at the perihelion, okay, meaning the closest distance to this one here, then you see that that distance is only 17 light hours. The period of the orbit is 15.2 years, and there's only 17 light hours. Now you see that if it were any reasonable extended object, reasonable extended object, it would be much larger. You have to squeeze the object in a very small radius compared to the 17 light hours, because if it were extended, it would affect the shape of the orbit, which could have been measured. It was not measured. So you know it's a compact object, and a number of arguments can be given to say that it is a supermassive black hole. Right. So, so now I will because I'm coming to the end of my time. I will quickly move forward in just a couple of minutes, and you see here the kind of problems that you can come across in a measurement. So you see that you are measuring the magnitude of the star S2 over a period of time, right? And then you see that the magnitude is fluctuating. Now, why is the magnitude fluctuating? It could be simply because it's a variable star, but it turns out that that argument is not really tenable. And therefore, what happens is that the magnitude is fluctuating because you are sometimes getting another star in the field of view, which is not resolved from the first star. Right? So, which means that what you think is the position of S2 could be a position of another star. And so that has to be discussed. So let's move forward now to another modern result. This result is 2009, where they further followed the ellipse. And what do they find here? I mean, just look at the point where my cursor is. You'll see that the ellipse is not closing on itself. And the things are so precise that you can say that this non-closing is not because of the error of measurement. So what is it due to? They said that it is because this supermassive black hole, which is believed to be at the focus, they said that it is moving, it is jiggling a little bit in the gravitational field, in the ambient gravitational field. And if it is jiggling, then the orbit jiggles too. So that was the expectation. Then we move forward. Come on. We move forward here. Now, this is just a comparison. I told you that there are two groups which are working on this. The blue measurements are by one group and the red measurements by another group. And this comparison is very good because it shows you that these difficult measurements are all being done properly. And so now we come to a measurement which was published in April 2020, meaning about 2 months ago. And the measurement was finished in 2019. You again see this marvelous ellipse here. That the ellipse is not overlapping, but now it is possible to put a limit on the movement of the cross, the supermassive black hole at the cross, and you find that it is less than 1 milliarcsecond, and which is completely insufficient to cause this non-overlap. So what does the overlap cause by? It is caused by what is known as Schwarzschild precession. So how marvelous. So you see that you have, I'm sure, heard about the precession of the perihelion of Mercury, which happens because of a general relativistic effect, which comes into play when Mercury is at its perihelion at a relatively short distance from the Sun. Exactly that is happening here. Over the course of 20 or 30 years of measurements, the thing has gone down more or less twice. Okay, and then because I told you that the period is about 15.6 years, and it was going to go through the perihelion in 2018. So they developed a new device which is called gravity. And that device takes light from all the 4 telescopes of the VLT and combines them together in phase. Okay, and which allows you to measure the positions even more accurately. So how accurately? And look at this thing here. So you see that these are the original measurements in 1995, and it is about the RMS uncertainty is about a few milliarcseconds, the milliarcseconds here, and these are the positions in 2019. So you see that the RMS accuracy is more like a 0.1 milliarcsecond. So you have developed, so you have gone from more than 1 to 0.1, less than less than 0.1, and therefore you have got about 10 times 10-fold improvement in the accuracy. And that 10-fold improvement in the accuracy allowed you to actually fit the orbit using general relativistic effects. They even see the gravitational redshift in the light coming from the star S2, which is a first order, which is what the PPN order 1 effect, PPN order 0 effect, and then the precision, the next order PPN effect, and that has also been detected. So I hope I have conveyed to you some of the excitement which comes out of becoming more and more precise. So here, let's see if I can show this to you. So here is the artist's impression. So this is a black hole. This is the event horizon of the black hole, and then 4 million solar masses. And this is the star S2, which is coming here, and this is the perihelion of the star. right? And then let's see here. Yes, here you can see artist's impression of the precessing orbit. Now, I finished my talk, but let me just try to show you a movie on this one. Let's see if it works. Right, it's coming in. So you see that as the object moves closer and closer to the black hole, it moves faster and faster, passes the perihelion in a flash, sort of, and then you see that the orbit is not closing along itself, and the orbit is slowly precessing. That's all. Thank you very much.
Ajit, quite a few students have asked for the slides. Is there any way you can share them?
Yeah. So what we'll do then, let's talk about that offline and decide that, okay? Yeah. Is there an echo?
All
Is
right.
there a deep echo?
Junie, can you raise your hand?
Yeah, I got that. I heard that. So what I will say is that I will talk to you about that offline, and then we will decide.
Yeah. No. We are going to the first question. It's by Junik.
Okay.
Hello,
So
sir.
he'll
Good
ask
morning.
the question.
Good morning, sir. Am I audible?
Yeah, you are audible.
Oh, thank you, sir. So my question is that the bar galaxies that you just discussed in the beginning, how stable are those bars? Like for how long they are stable inside in those galaxies, and what is the reason that they are sustained? Like, is there any time limit for which they stay, and after that they just like they just mix up and they just diminishes? Is there anything like that?
Yeah. See, sorry. Look, there's a. I got your question, please. I have understood your question. Yeah. Yeah. Okay. Let me. No, can I say something, please? Can I say? Let me say something. There is a echo. There's not an echo, but I'm getting two or three streams of the same question. Yeah. Ah, there's a delay. There's a delay on the line.
Hello.
Junik, can you mute yourself?
Yeah, definitely, sir.
Okay. Can I talk now?
Yes, Ajit, please go ahead.
Yeah. So, so you see that the question of the bar was a very good question, and it's a very important thing in the properties of the bars. The bars appear there, and they could last for let's say I don't know the number precisely, but tens of millions of years, or even 100 million years, and then they could dissipate.
Junik, do you have anything else to ask?
Yeah. Can I have a second question if I could?
Yeah, go ahead.
Okay. First of all, thank you, sir, for the first question's answer. That was really helpful. My second question is that there are some, when we are observing a galaxy, there is often a time that we observe the galaxy from the side views. So often from the sidewise, they just look like a bar or they just look like flat. So how does we differentiate between them and actual, like how does we classify that they are actually bar galaxies or they are not? Is this by like using those neural network systems? So was that one audible?
Yeah, you see, See, the thing is that I need to somebody, please. Can somebody give me a phone call, please? Can somebody call me on the phone, please? Can somebody
Yeah, I
call
can
me on
call
the
you.
phone, please? I said just keep.
I'm calling you, Ajit.
Call me on the. Just read it. One out of three different streams. Okay, so when somebody says something, it again repeats after a little bit of time. Then whatever I say gets reflected back to me after a little bit of time. It's not just words, but my whole sentences are coming out again. So there is something now. Yeah, so now you see, yeah. Now you know that somebody called me on the phone, now it is coming up 3-4 times it came. Huh? So okay, I'll try that. So just hold on to the phone. What I have to do is to uh, unmute. Speaker now.
Everyone, please hold on. There is a problem. We are trying to resolve it.
unmute. Yeah. Then what I will do, I'll go back to the, yeah, photonics built in. Yeah. Okay. Can you hear me now? Hello?
Yes, sir, we can hear you.
All right. So what, I answered the question about bars. Let us go to some other question.
All right. The next question is by Arjun, and he's asking that while measuring the Hubble constant over a large period of time, is it possible that the H naught value will change over that time?
So I'm sorry, everything that I have said over the last 10 minutes is being repeated on my loudspeaker. Srijit?
Yes, but we can hear you, sir. So
Yeah, okay, you hear me. All right, then I'll
yeah,
just
yeah,
go.
you can just answer that
Hubble
offline.
constant.
You can reduce your volume and answer it.
Yeah. So
Okay.
you see that the Hubble constant will definitely change with time. And so, for example, the time scales will change, everything will change. It's a very slow rate of change. And that rate of change is given by what is known as the deceleration parameter. Okay, so there's a parameter called Q double dot. So that carries information, the Q which carries information about the rate of change of Hubble's constant. That can be measured.
Okay. Then the next question is about it's by Pooja. She's asking that can we distinguish the barred and unbarred galaxies in some other way? Like apart from bars, is there any other way we can also distinguish?
Yeah, you see, that these questions are all really very good. Now you see that the bar has arisen because of certain processes which are gone inside the galaxy. Right. So now we are not, I mean, we are seeing thousands of bars now. That is not the point. The point is understanding those processes, meaning that is the bar caused only by processes inside the galaxy? Is it caused by the presence of other galaxies in the neighborhood and perturbations and so on and so forth? Does it happen more often in bright galaxies than in faint galaxies? And that is what we are trying to study. And once we do that, then we may find other phenomena which are which are associated with uh, the reason why the bars were formed. Right? So that is the point in studying so many barred galaxies.
Okay. There's a question from YouTube by Madhusudan Purohit. He's asking how people fix frames for references for measurement of positions of stars and how they transform the coordinates.
Now, how do we fix frames of reference? You see that is not something which I can explain to you. So you see, for example, yeah.
I think that's all. I mean, there are no more questions now.
Okay, all right. Thanks.
Thanks.